All right, folks, for our final video of the kinetics chapter here, we're kind of going to get a mixture of some topics that probably don't seem to go together real well. But we're going to finish up with temperature dependency as far as kinetics goes. We're going to finish up with the process of reaction, specifically what exactly a transition state is, and then finally the process of catalysis. So a quick slide here to illustrate temperature dependency and the rate constant. So there are two things that will change when the temperature changes when it comes to kinetics. The actual rate, which according to the collision theory, we predicted that the rate would increase if we increase temperature due to an increased likelihood of colliding with enough energy to overcome the activation energy. So it's very important that we understand this. See it in multiple choice questions all the time. Questions to the effect, which of the following will change when temperature changes? And the two things in kinetics that will would be the rate, the actual rate itself. So we're talking this part of the rate law right here, okay? The rate will change when temperature changes, as well as the value of the rate constant. So it's so important that when we say rate constant, you understand that it's only constant at the stated temperature. Be careful. That's why you always see in kinetics problems, they're going to have to state the temperature because they want to be correct as possible in these questions. And they want to state specifically that we're talking about this specific temperature and no other temperature. So in general, both the rate and the rate constant increase as temperature increases, simply to fulfill the algebra really of this equation here. We know that the rate increases, so therefore to make the rate increase, the rate constant also has to increase itself. And as we talked about, this does coincide with the collision theory or the collision model. Okay, so there's an equation that I still talk about, even though it's not a very common equation to show up on the AP exam. In fact, I haven't seen it show up on the AP exam in the 5 years I've been teaching the class. So what that equation is called would be the Arrhenius equation. And what this is a way for us to quantify how the rate constant changes with temperature. So when we see a temperature change, we can calculate the new rate constant. And I don't normally spend a lot of time on this because I've never seen it. We get the activation energy right here. We get the universal gas constant, but it is important if you join me down here to note that that is not the 0.06 number that we use for gas laws. This is the gas constant that features a unit of energy down here. Again, not something that shows up very often, so I don't spend time on it. And as I said, in the 5 years I've been doing this, I have not seen this once on the free response section. So I suppose we just need to be aware that it is possible to calculate the new rate constant should the temperature change. Okay, a little on activation energy. So we go back to this graph that we saw on day one. We can see another exothermic reaction. Once again, we know that this is exothermic because it is a graph that features the products at a lower energy state than the reaction. So energy must be leaving. Okay, so as a reminder, this is the minimum energy that the collision must experience in order to turn reactants into products. Now, it is important to note that when you increase temperature, this stays constant. So on those multiple choice questions where what is temperature dependent, activation energy is usually a choice that you could potentially choose, A, B, C, D, or E. You want to avoid that. No matter what, activation energy changes only if you add a catalyst. Okay, so the only time an activation energy can be changed is through the addition of a catalyst. So what we get here is basically two graphs where I want you to recognize one is exothermic and one is endothermic, but what we're getting to here is the ability for you to calculate the activation energy. So if you happen to get a value here and a value here, the difference of those would be the activation energy. So moving forward, what specifically this means, okay, is I'm going to show you a picture of a roller coaster here, and it's kind of ambiguous what actually happens, as we travel up this slope right here. Is nothing happening? Is there any interactions that are changing, or is it just a big bunch of nothingness until we get to this specific spot that is the top of the hill, if I can? So the answer is no. Actually, a lot of stuff is happening. What happens when we get to the top of this hill here is we are currently and constantly forming what we call activated complexes. Okay, and as we climb up the hill on that graph, we're constantly forming activated complexes. Bonds are trying to form, they're trying to break, but only when we get to the top do we get to what we call a transition state. Okay, so there are a lot of activated complexes, but only when we get to the top do we get the highest possible energy activated complex, and only when the transition state is formed do we get reactions. So this down here, this statement can only be made when we are at the very top of this hill, because by definition, transition state is the highest energy activated complex. And once we get here, we've reached the point of no return. Once we're at the transition state, we're at the point of no return, and we're going to go ahead and make products. Now, I want you to notice kind of what a transition state looks like. It doesn't look like a normal chemical compound. We've talked about organic compounds here. We've got a carbon at the center there, and it looks like we've got 1, 2, 3, 4, 5 things bonded to that carbon, which we know is not possible. Carbon can only bond with 4 things. And this is kind of the confusing part about kinetics, because during this change, things don't behave the way that we normally expect them to behave. So what kind of happens is we get this new bond forming right here while this bond is breaking, but for a split second it appears that all 5 of these things are connected essentially, and what will happen is obviously this hydroxyl group will eventually kick off this bromide ion. So we've got these activated complexes that are forming all the way up this particular activation energy graph, and once we reach the top, we then get what is known as the transition state. Okay, so again, it's correct to call a transition state an activated complex. The transition state is the highest energy activated complex. It is not always correct to call an activated complex a transition state. You can only call it that if the particular activated complex you're referring to is the highest energy activated complex. Okay, so an intermediate, we have to understand that an intermediate is not the same thing as an activated complex or a transition state. An intermediate looks like something like this. Maybe this right here is not the final product of a reaction. Maybe this is one of the intermediates that form in one of the elementary steps of a mechanism. So this is not an intermediate right here. This is just a goofy kind of middle ground, if you will, for a new substance to be formed. Intermediates are actual viable chemical compounds like you see right there. So an intermediate is simply something that is going to be produced and then reconsumed. So in order to form these things, you do still need to have activated complexes and transition states, but they are not correct. It's not correct to call these things the same things, because intermediates are viable chemical compounds, meaning they follow things like the octet rule. They can actually have a Lewis dot structure. They just may not be the final product.